Hey everyone. There we go. In this video, we're going to go over our reference graphs. You need to be really, really comfortable with these reference graphs. Not comfortable like I know they're written down on a piece of paper and I'll be able to go look at that piece of paper, but like you have all this knowledge in your head. Um, I would be prepared for uh, certainly a quiz on everything above that line, the reference points and the sketches of each. These are going to be like knowing your multiplication tables in elementary school. So why don't you go and pick up assignment 3 in class reference graph chart from the Office 365 site, and you can be filling this out while I go through it. Okay, so we're going to start with these reference graphs, and like I said, they're really, really important. And in fact, all the stuff we're going to do for the next, I don't know, almost week is going to depend on these. But we'll be using these reference graphs not only this semester, but also next year in Calc. So really, really important to get comfortable with these. Okay, so the first one is y equals x. And y equals x passes through -1, -1, 0, 0, 1, 1. And those are your reference points. And the graph is just that equation that goes through the line that goes through the origin. It passes through 1, 1, 0, 0, and -1, -1. Okay? Domain for the reference graph. Well, this graph goes forever. I can plug in any x value I want here, and I'll be able to get any y value out. So we're going to say that the domain is from -infinity to infinity. I can plug in any real number and get a point on my line. The range is all the possible y values. If the domain is all the possible x's, the range is all the possible y's. So this is going to go up forever, which means I'm going to get all these y values. And this is going to go down forever, which means I'll get all these y values. And so my range is also -infinity to infinity. Okay, increasing, decreasing. Well, this graph, because it has a positive slope of 1, right? This is a 1x. This graph has a slope of 1. It's a positive slope. So this graph is always increasing. I know a function is increasing when the slope is positive. If I see a positive slope, the function is increasing. And so our graph is always increasing from -infinity to infinity. Decreasing, however, I would need a negative slope. I don't see any negative slopes. I don't see any going downhill on this linear equation, y equals x. So decreasing is just never. Never decreasing. Okay? So there's our first reference graph, y equals x, the linear equation. The next one is y equals absolute value of x. This passes through 1, 1 and 0, 0, just like the linear equation did, but instead of -1, -1, it passes through -1, +1. Our reference graph, therefore, looks like this, passing through 1, 1, 0, 0, and here, -1, +1. Now, mind you, this is coming from y equals x, but because of the absolute value, all this negative stuff is reflected up. That's how we should think about absolute value of x. It's just going to flip up this negative portion. And so instead of passing through -1, -1, like y equals x does, it passes through -1, +1. So there's our reference graph. What about the domain? Well, again, I can plug in any x value that I want here. Negative 100, positive 3000, 62, any number, I can plug it in and I'll get a y value out. So I'm going to say that the domain is, again, all real numbers. The range, however, isn't all real numbers. It doesn't go from negative infinity to infinity. Range is all the possible y values. So when I look at what's the lowest y value on my graph, 0 is, and 0 is included. So we're going to say the range is bracket 0, and then it goes up forever. I can get all these y values. When do I use a bracket? I use a bracket when I'm saying that that value is included. Infinity, you can never get there, so it'll never be included. Infinities always get parentheses, whether they're positive infinities or negative infinities. So let's take a look then. We've got domain and range. Let's take a look at increasing. Well, we said when there's a positive slope, we would be increasing. And when there's a negative slope, we'd be decreasing. So on this part of the graph, we're increasing, and on this part of the graph, we're decreasing. So I'm going to say increasing on 0 to infinity. These are x values, by the way, from x equals 0 to x equals all the way out to infinity, which means I go forever. And I'm decreasing from negative infinity until I get to 0. Negative infinity to 0. Now what about 0? Well, I can understand why you might want to put a bracket here and put a bracket here. But if you do that, what you're saying is that 0, x equals 0, is a place where the graph is both increasing and decreasing. And that just isn't true, because we said if there's a positive slope, the function is increasing. Well, there's not a positive slope here at x equals 0. Here, just to the right of 0, that's a positive slope. So I'm going to say up to 0, but not including 0. And likewise, decreasing. I'm decreasing until I get to this x value of 0. At 0, I'm neither increasing nor decreasing. So I want to have a parenthesis there for decreasing. Okay? So we had our reference points, negative 1, 1. Here are our reference points. Here's our reference graph. Here's our domain and range. And this is increasing and decreasing. By the way, this notation is called interval notation that I'm using here. And this is what we're going to be doing. We're not going to be using inequality notation for domains. So I'm not going to say something like x is greater than 0. No, frowny face. Instead, I'm going to be saying 0 to infinity. Ooh, smiley face. Okay, and we'll talk a lot more about interval notation. I'm just introducing it gently now. I think in 3-4 more videos, we'll really dig into it. Okay, so our next reference graph, y equals x squared. Well, this one has the reference points, negative 1, 1, 0, 0, 1, 1. Now, you may notice that these are in fact the same reference points that we had for y equals absolute value of x. So it's not going to be sufficient just to know what the reference points are. I also have to know what's the shape of the graph. And this is the shape of y equals x squared, our parabola. It passes through negative 1, 1, 0, 0, and 1, 1. Okay, as opposed to absolute value of x, which passed through those same points, but had a very different shape, right? So you need to make sure you know the shape that goes along with your points. So here are our reference points, negative 1, 1, 0, 0, 1, 1. And here's our reference graph. What about the domain? Well, again, I can plug in any x value I want here. So my domain is going to be negative infinity to infinity. And what about the range? Well, just like absolute value of x, the lowest y value is 0, and 0 is included. So I'm going to say the range is from 0 to infinity. And when I think about domain, I'm looking at this. I'm looking at all the possible x values I could plug in. When I'm thinking about range, I'm looking this way, and I'm thinking, okay, what's the lowest y value and what's the highest y value? The lowest one is 0, and then this function goes up forever to infinity. 0 is included, so we get the bracket there. And then finally, we've got increasing and decreasing. Well, I see positive slopes over here, so this function is increasing on 0 to infinity. And I see negative slopes over here, so this function is decreasing from negative infinity to 0. When we use interval notation, we always put the smallest value first. 0 is smaller than positive infinity. But the smaller value here is negative infinity. That's much smaller than 0. So that's why I'm using this. Please don't write this, because that doesn't make any sense in my brain. I'll mark that wrong. Okay? All right, so there we've got y equals x squared, our parabola, our basic parabola. Next, we've got y equals x to the third. Okay, so y equals x to the third has these reference points, -1, -1, 0, 0, 1, 1. And you may recognize these reference points as the reference points that we had for y equals x. It passes through the same points. But the shape is different. It starts looking like a parabola over here, and then an upside down or a reflected parabola over here. We pass through 1, 1, we pass through 0, 0, and we pass through -1, -1. These are our reference points on the reference graph. And by the way, when we quiz over these reference graphs, we're I'm going to need you to label not just the reference points somewhere on the piece of paper, but they actually have to be labeled on the graph. Why? Well, over the years, I've had lots of students who, when they wrote them here and I asked them to point to the place on the graph where that point would be, they would point to the wrong place. So it's not sufficient just to have the reference points here. If we have a quiz, you need to have the reference points on the graph itself, okay? Also notice I'm not making little hash marks here. Oh God, please don't do this kind of thing. It's such a waste of your time, and it's just not a good scale. These aren't all the same distance apart. It distorts, and you're going to have a devil of a time trying to fit your graph to that. Know the shape, draw the shape, and just throw the points on it. It's much better. Okay, so what do we need to talk about here still? We need to talk about domain for the reference graph. And my domain is, just like y equals x squared, I can plug in any x value I want and cube it. So I'm going to say from negative infinity to positive infinity. What about the range? Well, the range, again, is all the possible y values. This goes down forever, this goes up forever, and because of that, we say that the range goes from negative infinity to positive infinity. These are two different things. This negative infinity means way over there, whereas this negative infinity means way down here, okay? And then what about increasing and decreasing? Well, I see a positive slope, a positive slope, a positive slope. And then I see a positive slope over here as well. The only place I don't have a positive slope is at 0, because really what's happening here is that I have just at that point a 0 slope. So this function is increasing from negative infinity to 0, union 0 to infinity. I have to write it in two pieces because I don't have a positive slope at 0. Decreasing? Never. This is never decreasing. This is always increasing or a slope of 0 at x equals 0. Okay. Next reference graph. We've got y equals square root of x. Okay, so here's a function, y equals square root of x, that has a restricted domain. I can't plug any x value I want in there. If I try and plug -1 in there, I get an imaginary number. So we're going to be using 0, 0, 1, 1, and 4, 2. Why 4? Because the square root of 4 is 2. If I used 2, then I would have to have square root of 2. And many people are uncomfortable trying to graph square root of 2. So we're not going to try and do that. We're just going to use these nice whole numbers here. So these are our 3 reference points. And our reference graph looks like this. 0, 0, 1, 1, 4, 2. There's our reference graph. Note, it stops. This graph does not continue, does not do anything else over here. There's nothing past this. So when I think about the domain for this function, I go from 0 to infinity. So bracket 0, comma, infinity. And when I think about the range, I go from 0 to infinity. This is rising. It's rising slowly, but it's going to continue to rise as x heads towards infinity. So 0 to infinity. When is this function increasing? This function is increasing everywhere on its domain. So from 0 to infinity. And decreasing, never. This function has a positive slope everywhere, including at x equals 0. At x equals 0, it actually has an infinite slope, but it's a positive infinity. So we're going to go with is included for increasing there. All right, we've only got a few more left, 3 more reference graphs left. We had square root of x, so now let's have cube root of x. And a cube root of x passes through the same reference points as some of our other functions. Have we seen these reference points before? Where? That's right, we see them in the linear model, y equals x, and that's right, also y equals x to the third. Be careful. A lot of people, when I ask them to graph cube root of x, they graph y equals x to the third. We want to be really careful that we use the right shape for the given function. So cube root of x looks like square root of x over here, and then the reflection over here. So we're passing through 1, 1, we're passing through 0, 0, and we're passing through -1, -1. This is y equals cube root of x. Don't confuse this with y equals x to the third. The green one is y equals x to the third. And I'll say a lot of people on quizzes, I ask for this one, they draw the red one. I ask for this one, they draw the green one. No. Make sure you draw the correct shape through those reference points. You really need to know this. You really need to be clear as to what the shape is, okay? So, cube root of x is the one that kind of looks like a square root with a reflected negative square root over here, as opposed to x to the third, which looks like that parabola shape x squared, but also a reflection of it, all right? So, y equals cube root of x passes through -1, -1, 0, 0, and 1, 1. Just like y equals x. y equals x draws through those points as well. So make sure you know this shape. And what about domain? Well, the domain here, unlike square root of x, which has a restricted domain, no negatives, the domain for cube root of x is negative infinity to positive infinity. I can plug in any number here. The cube root of negative 8 is going to be negative 2 times negative 2 times negative 2, or negative 2. Look, cube root is okay taking a negative number in. That's not an issue like it is for square root of x. So don't say, oh, well, it's a root, therefore it's got a restricted domain, because that's not true. Okay? So what about our range? Well, our range, this is going to go down forever. This is going to go up forever. So negative infinity to infinity. And then we need to talk about increasing and decreasing. Well, this graph has a positive slope everywhere. Here at x equals 0, there's an infinite slope. So I'm going to say increasing, negative infinity to infinity, and decreasing, never. Okay? Next, we've got 1 over x. Now, 1 over x is different. It is different. We're going to take and do a little mini unit on rational functions. When we see fractions with algebra with x's in them, we call that a rational function. And we'll do a mini unit after that, after we take on our unit about polynomials. So what does this look like? Well, this one does pass through 1, 1, does pass through negative 1, negative 1, does not pass through 0, 0. Instead, this graph has something called asymptotes. It's got a horizontal asymptote, HA at y equals 0. It's got a vertical asymptote, at x equals 0. Remember, we said in that earlier video that x equals a number is a vertical line, and y equals a number is a horizontal line. Now, these asymptotes are what the function bends to. They're like gravity sources, and so we bend to that asymptote, and we bend to that asymptote. And the same thing happens over here in third quadrant. We bend to that asymptote, and we bend to that asymptote. So I need to see all of this on your reference graph. I need to see the two reference points. I need to see the asymptotes, and I need you to label the asymptotes as well as the points. Make sure you know the shape that goes through those points as well. Okay, the last one we have, I think it's a little cut off. It should say y equals double bar x. What's that? Well, it's not absolute value. We already did absolute value. So this has got to be something else. And what it is the greatest integer function, sometimes called a step function. I like to think of it as the rounding down function. And the reason I think of it as the rounding down function, because when I plug in 0, I get 0. But if I put in 0.1, that rounds to 0. And 0.5 rounds to 0. And 0.9 rounds to 0. And 0.999 rounds to 0. But as soon as I get to 1, I'm at 1. And 1.1 would round down to 1. And so we're going to end up with a graph that looks like a bunch of stair steps. Now be careful, because at 0 we have a closed circle, and we go out to 1 with an open circle. And then we jump up at 1, because at 1 the y value is 1. And then we go over another 1 to an open circle at 2, and then we jump up another step up to 2. And this continues both in the positive direction and in the negative direction. So here at negative 1, it would look like this. And at negative 2, we would have a graph that would look like this. negative 2. Okay, so there's our reference graph for int x, the rounding down function. Notice at 0 the value is 0, at 0.1 the value is 0, at 0.5 the value is 0, at 0.9 the value is 0, even at 0.999, right up here, the value, the y value, is going to be 0. It's not until we get to 1 that we step up to a y value of 1. And then 1.1 is also 1, and so on. Okay? This graph, yeah, so when I think about the domain, I think, okay, I have all these x values, but I don't have that one. Oh, yes, I have that x value up there. So that takes care of not having it down there. And then I go over and I have all these x values, but I don't have that one. Oh, yes, I do up here. And so my domain is actually all real numbers. Negative infinity to infinity. My range is really hard because I don't have any of these y values or these y values or these y values. So I'm never going to ask you about the range here. But if you wanted to say something about the range, I would say the range is the set of integers. Yeah, again, I'm not going to ask you that, so don't worry. I don't see any positive slopes here or negative slopes here, and so even though this graph is going up, this is not an increasing function. So when it comes to increasing and decreasing, yeah, I'm not going to be writing anything for that. Increasing, no. Decreasing, no. Because these are all little horizontal segments with a slope of 0. Okay? All right. So those are our reference graphs. And if we were in person, I would be giving you a pop quiz on those tomorrow. Hey, we may have a pop quiz in our Zoom tomorrow or whenever our next Zoom is. So be prepared for that, okay? I feel like that is a lot of stuff if I want you to actually memorize it. So I'm not going to do any more new stuff in this video. I would like to take a few minutes to review some of the things that we've talked about so far so that we're ready for our first big quiz whenever that comes. Okay, so here's your question. Y equals 2x minus 3. And I want to write the equation of the line perpendicular to the given line, and by the given line I mean that thing over there, through the point, and I'm going to give you a point, 1, 4. Okay, we did this in the last video. You should be comfortable doing it. Why don't you pause this video and see how it goes. Give it a try. Come back when you're done. Okay, so welcome back. If I want something perpendicular, I need the opposite reciprocal slope. I see the original line has a slope of 2. So my perpendicular line would have a slope of negative 1/2, opposite reciprocal. So using negative 1/2 and 1/4, I'm going to write the equation of the line using point slope form. I'm going to plug this in for x1, for y1, and for m perpendicular. So y minus 4 equals negative 1/2 x minus 1. Now I want to tidy this up. I want it in y equals or slope-intercept form. So I'm going to start with distributing this negative 1/2. Make sure that negative times that negative turns into a positive. And then add 4. And so I get y equals negative 1/2 x. 4 plus 1/2 is 4.5 or 9/2. And so there's the equation of our line. This line is perpendicular to that line, and this line that's perpendicular to that line, this line passes through that point. Okay, so 2 more. How about write the equation of the line parallel to y equals 4 through the ordered pair 5, negative 3. Well, what do we remember about a line y equals a number? Y equals a number is going to be a horizontal line. Here's the line y equals 4. I want to write the equation of the line parallel to this one, but we have to pass through this, oops, wrong color. We have to pass through this point, 5, negative 3. So again, my slope will be 0. Again, I'm going to have a horizontal line because I'm parallel to that one. And again, I need y equals a number. What number? Right here. The y value of the point we're supposed to pass through. So parallel to this, passing through that, would be y equals negative 3. This line is parallel to this line. They both have the same slope of 0. But this line passes through this ordered pair. Okay? What if we change that to be perpendicular to y equals 4? Well, perpendicular to a horizontal line is a vertical line. And so I want to write the equation of this line, 5, negative 3. What was the equation of any vertical line? X equals a number. What number? This number, the x-coordinate of the point we're supposed to pass through. So what's the line perpendicular to y equals 4 that passes through this point? That perpendicular line is going to be x equals 5. X equals 5 is the line that's perpendicular to y equals 4 that also passes through the point 5, negative 3. Okay, last thing I want to do is a little word problem opportunity. Some of you may have been to Lake Powell in northern Arizona. It's where a lot of the water from the Colorado River is, and we get a lot of our household water, our farming water from the Colorado River through Lake Powell. Lake Powell's water level has been dropping. And when Lake Powell's water level drops too far, we won't get any more water here. So in 1999, the water level in Lake Powell was 3,700 feet deep. That's pretty deep. Then in 2019, the water level was 3,575 feet. So we see that the water level had dropped 125 feet in those 20 years. Okay, so we're supposed to, part A, find the average rate of change. Well, we said before that average rate of change is just slope with units. So let's pull out our slope formula. M equals y2 minus y1 over x2 minus x1. And these are our outputs, so they go on top. These are our inputs, they go on the bottom. 3,700 minus 3,575 over 1999 minus 2019. So I get 125 on top, and on the bottom, negative 20. Or, as your middle school math teacher tried to get you to understand, that would be the same as negative 125 over positive 20. Right? And so how am I to understand this? Well, the units on top are feet, and the units on the bottom are years. And so I want to understand this as the water level is decreasing by 125 feet every 20 years. Okay? Now I see that I can divide 5 into each of those. So that's going to be 5 goes into that, 20, and is it 25? Yes, it is. 25 feet every 4 years. Okay, there's my average rate of change. Every 4 years, the water level seems to be dropping 25 feet. Any questions about finding average rate of change? Well, if you have them, make sure you ask them in our next Zoom or send me a message in our GroupMe. Okay, next question. Write a linear model. Write a linear model d of t, where d is the depth in feet and t is years since 1999. That means t equals 0 is 1999. So I'm going to be thinking about this information here in this table as some ordered pairs. My first ordered pair is time equals 0. We have 3,700 feet. My second ordered pair, how many years after this one is this one? 20 years later. We have 3,575 feet. So now I've got these two ordered pairs, and I want to write a linear model for the depth as a function of time. Well, that's easy. We know already the slope, the average rate of change. We found out that that average rate of change, m, was equal to negative 25 over 4. So there's my rate of change. Here's my initial amount. So I can just write d of t equals rate of change times the input variable plus the initial amount. There's my depth of water model, right? Remember what we said when we were doing linear word problems. The output, the ending amount, is the rate of change times the input variable plus the original amount. I know the original amount here because I defined t equals 0 as 1999. Okay, so the last thing I want to do with this data is predict when Lake Powell becomes a dead pool, i.e. Tucson doesn't get any more water because the water level is too low. And the hydrologists say that occurs at 3,370 feet. At 3,370 feet, there won't be water coming down to Tucson anymore. So, unless we do some really dramatic changes to the geology up there. So, we've got our model, and I want to know when our depth is equal to this. So, does this number go in for t or d? Is this a time or is this a depth? That's right, this is a depth, so I'm going to say 3,370 equals negative 25 over 4t plus 3,700. Why don't you pause the video and solve this equation for t and come back when you're done, and we'll check our answer. How much time do we have to enjoy Lake Powell before it becomes a dead pool? Welcome back. So in solving for t, I'm going to subtract 3,700, and I'm going to get negative 330 equals negative 25 over 4t. And here, I could multiply. You know, a lot of students say they want to divide both sides by this. And I think that's a little crazy because now you're taking this number and dividing it by a fraction, and it just means that you're going to get confused. So instead, why don't we just multiply both sides by 4? Because then that will cancel out that. And at the same time, divide both sides by negative 25. Because then that will cancel that. I.e., what did I do? I multiplied by the reciprocal. Multiply by the reciprocal to clear that out, but do it to both sides of the equation. Okay, so we can cancel out these negatives. 25 into 330, well, I don't know about that. I do know that I do know that 5 goes into 330, but I don't think 25 does. So 330 divided by 5 gives me 66. And 4 times 66 gives me 264. And I took a 5 out of each of these. And so I have a 5 here. If I do this division, 264 divided by 5, I get 52.8 years after 1999. Okay, when is that? So if I do 1999 plus 52.8, that gives me 2051.8. So sometime in the year 2051. So you're gonna be in your, let's say you're 17 now. Ooh, yeah, you're still gonna just be an adult. This is definitely within your life that we could run out of water. So watch out. Pay attention to how much water is in Lake Powell. It will affect your life if you stay here in Tucson. All right, well, I hope this video was helpful. The homework tonight is this homework assignment here, assignment number 3. There are, of course, some pages to read actively, and then there's some book work to do. Make sure you label 3 points on each graph, as you should on all graphs if you want credit. Not off to the side, but on the graph itself, right? No credit if you don't label those graphs. Thank you. I will put the scanned version of these pages up into Office 365 in our pre-cal team for you, so you can get to work on that. I hope this was helpful. Have a wonderful day.